You've probably seen one of these. It's a fidget spinner. They were all the rage a few years ago. They have some interesting application to our current topic. Let's just watch how it works. You just spin it and you can hold it and play with it. That's about it. They're pretty stable and they'll spin for quite a while if you let it. Something interesting happens though if you add a little bit of mass or weight to one of the sides. So here I've just taped on a drill bit. You saw how stable it was in its natural form. Let's see what happens now. Alright, noticeably different motion now that I've added a little mass. Well, you could call this a balance problem, and that'd be fine if you do, but I'm going to call it a center of mass issue. Okay, so let's go ahead and define center of mass as the average position of all the mass that makes up an object. You may have heard the term center of gravity. And technically speaking, those are two different quantities. But in all reality, for almost every situation we'll find ourselves in, they mean the same thing, and so we're just going to treat them that way. I won't bother defining the difference, and I'll use the two word terms interchangeably. This is an image that was taken with a high-speed camera. Somebody threw a wrench really hard across the room, and you'll notice the kind of loopy pattern that it makes as it rotates through the air. But one thing to really pay attention to is there seems to be a point on the wrench that travels, if I trace that out, it's almost a straight line as that wrench flies through the air. Well, that point is the center of mass of the wrench. And what we can observe from this, and the observation we're going to take from this, is that a freely moving object will rotate about its center of mass. The overall motion of any object as a whole will act as if all the mass was located at the object's center of mass. So what I'm saying is if we took this wrench and squished all of its mass down to a single ball, that ball would have the same motion as the center of mass for the wrench when it's fully shaped like this. So that's what I mean by the object as a whole will act as if all the mass was located at that object's center. Okay, but if the object is free to rotate like this wrench was, then it rotates about that center of mass. That's what all objects want to do if they're rotating. They want to rotate about their center of mass. So if we go back to our fidget spinner, in its natural state, it's a symmetric object, and the mass is distributed in such a way that the center of mass should be right at its geometric center. When I rotate it about that point, it wants to rotate that way anyway, so it's nice and stable. When I throw off its mass, I've now shifted the center of mass that way, so this is the point the object wants to rotate about. But the way I rotated it, it was making it rotate around its center, so that's what caused the instability. The object didn't want to rotate around its center, it wanted to rotate around this point. So that's what we call an imbalance. If you've ever had your tires balanced on your car, they're dealing with the same issue. If the center of mass isn't at the center of the tire, then that's going to wobble and it's going to cause other problems for your vehicle. So they shift mass around if necessary in order to line up the center of mass right in the center of your tire. That gives you a much more stable ride as well. Okay, so how do we find the center of mass? Well, turns out it's not so easy. It would require something like this. If you don't know what this is, these are vectors. And this is an integral, so this is vector calculus. And that's what you have to do if you actually want to find the center of mass of an object. Obviously we're not going to do that. I just wanted to point out the fun that you're missing by not taking the full class. Well, the nice thing is we can still make a lot of very useful and very practical observations without doing any calculus, so let's focus on that. So first of all, for symmetric objects of uniform density, the center of mass is simply the geometric center of the object, as I'm showing down here. The key to this is symmetry, but also uniform density. So you can imagine if this square here had extra density, so more mass piled up at this location, then that would shift the center of mass up towards it, so it wouldn't be the geometric center of the object. Fortunately, in the real world, there actually are a lot of symmetric objects with uniform density, so this is a useful observation. The fidget spinner isn't exactly uniform density, but the mass is distributed in such a symmetric way that it more or less qualifies for this. Now, to define the center of mass without calculus, we're going to have to make some more observations than just this, because there's a lot of objects that aren't symmetric or don't have uniform density. So what I'm going to do is I'm going to explain some key observations that have been made about the center of mass. So the first observation is that an object that is free to rotate will eventually come to rest with its center of gravity directly below the pivot. Well, let's go back to our fidget spinner. These are actually bearings, and so the spinner is free to rotate about any one of those as well. So the way I'm holding it, I'm keeping it off balance, and then I'll let it go and we'll see what happens. Okay, that didn't take very long. Remember, the geometric center was the center of mass for this object. So if I draw a line through my pivot point, you can see that the center of mass is directly below that. The reason why this shape wants to do that is actually because of torque. So we said that the gravity will act on the center of mass as if all of the object's mass was at that point. So for this example, gravity is basically treating this fidget spinner as if all the mass was right there. Gravity always points straight down, so if we use what we learned about torque, we can draw a line from our pivot point straight to where the force is being applied. That's our radial line, or our lever arm. And in that case, our lever arm and our gravity vector have zero angle between them. So the torque is zero. We say that the torque due to gravity is zero in that position. So that's why the center of mass will always settle directly below your pivot point. All right, so what I did here is I just grabbed a bunch of stuff I had sitting around, and I wanted to purposely throw off the mass of the fidget spinner just to test this idea to see if the center will still hang in the same spot. All right, so if I draw that line straight through my pivot point, you can see that the center of the fidget spinner is clearly not directly below anymore. So what that means is that the new center of mass for the total object must be somewhere along this line. So it's probably right there. So that means gravity is acting right there. And again, the torque should be zero. So our lever arm and our gravity vector are parallel, so zero angle between them. So we can say again that the torque due to gravity is zero in this position. Let's look at another observation. If you pivot an object at the center of mass, it will not rotate, even if it is free to do so. Let's go with the fidget spinner again. So this is the location I kind of pointed out that I thought the center of mass was. So I'm just lightly holding it at that point. It should be able to move if it wanted to. I'm just barely holding it just enough to keep it up. And when I let it go, here we'll play the video. I mean, nothing happens because there's no reason for it to rotate. Let's try this where I'm obviously at the center of mass, right in the center there. We'll play that. So even though it's free to rotate, there's just no reason for it to rotate. A similar situation is happening here. The torque due to gravity is zero in that position, but in this case, It's because the pivot point is at the center of mass. So in that case, the lever arm is 0. There's no distance between the pivot and where the force is being applied. So that's why the torque is 0. Let's go through another observation. This will be our last. If the center of mass is directly above a support base, the object will be stable. Let me show you what I mean by that. Okay, here I have just a random scrap piece of wood, and one end is cut nice and square shaped. The other end, you'll notice, has an angle to it. So I'm just going to set that up, and I'm going to set it on the flat end. And this is what I mean by stable. It's not wanting to tip over. So let's go through that. So the support base for that piece of wood is right down here. If I draw vertical lines directly above that, the center of mass of this object must be somewhere in this area. And it doesn't really matter where, as long as it's above what we call our support base. So let's just say it's about right there. If you notice, gravity is now pointing back towards our support base. So this would be another situation where the torque due to gravity is 0. So it's parallel to our radial arm. All right, now I'm going to flip the block of wood and try to stand it up on the angled part. And it falls over. Not too surprising. So what's the deal here? Well, our support base is tiny. It's just this little teeny point. So I'll just draw a little line straight up. So for this to be stable, the center of mass has to be somewhere directly on this line. And that's not easy to do. You can see I tried to balance out what I thought would be the center of mass right above that support base. But I must have failed. So what I'm showing here is, I know it's really hard to see, but I'm showing that the center of mass must be slightly off this vertical line so that there is a torque. So the torque due to gravity is not 0. And remember, torque is the ability of a force to change the rotation. So in this case, the torque is resulting in a change in rotation. The result of that was, of course, that it fell over. So in order to make this piece of wood stable, I need to either increase the support base or just shift it around so that the center of gravity is directly over whatever support base I have. So there's kind of a fun way to do that. I can actually add mass to shift the center of gravity. So I'm going to do that. I had a little trouble getting it in, but there it goes. And there we go. So notice it is free. It's standing up on its own, but it's stable. Let's figure out why this is stable. The support base is now this. Okay, if I draw vertical lines directly above, the center of mass of the combined object has to be somewhere in this region, and it really can be anywhere. So it really could be right there. I don't know for exactly, I didn't test it out, but my point is that the center of mass does not have to be physically located on the object. The center of mass isn't a real point. It's not a real part of the object. It's just a theoretical concept that we've used that works really well for describing motion. So there's no reason that the center of mass can actually be in open space like that. So let's say it was right there. Gravity is going to act, even though all of the object has a shape like that, gravity is really only going to act right there, and that's going to be straight down to our support base or our pivot point. So it'd have a torque of 0. Okay, I hope this was enough to really sink in why why center of mass and stability are really two concepts that go hand in hand. Here's just a couple more, I'll go through these much quicker, a couple of fun examples of stability and center of mass. In this case, I just have a hammer and a ruler and a string, that's all. If you play around with the combination of those three objects, you can create something that's awkwardly stable. You should try this one time. It kind of messes with your mind a little bit because it just looks awkward. All right, so in this situation, the base of stability is right there, just that tiny little point right there. The reason why it's not falling over is because the center of mass must be directly below, so it's probably right there for our system. That's all you need for an object to be stable under gravity. Maybe you've seen one of these. It's just a toy bird, but it's weighted in a special way. It's also gravitationally stable. It's just balancing right on its beak. There's that tiny little tip. So because it's gravitationally stable, that means that the center of mass must be right there. It's a little counterintuitive when you look at the bird because the shape certainly doesn't suggest that. It suggests gravitational or a center of mass back here. The trick to that is these wings are weighted with extra weight, so this is not a uniform density object, and thus the center of mass is in a location that's not the geometric center of the object. If you want a way to find the center of mass without hanging an object upside down or trying to see if it'll tip over, here's an interesting method. Bella here is holding a meter stick, so 100 centimeters, and it's just resting on top of her fingers. And what she's going to do is she's going to slide her hands in together at the same time and watch where her fingers end up. Okay, well, this is a symmetric object with uniform density, so the center of mass should be right in the center, which is 50 centimeters, and it is. The fact that it's balancing right now suggests also that it's pivoted at the center of mass. So you should try this yourself sometime. It doesn't have to be a ruler. Grab anything. Grab a broomstick. It doesn't even have to be uniform density. It wasn't her consciously moving her fingers at the same time to end up in the center of mass. It's just that's what the object made her do. Let me kind of show you what I mean. Now I've added extra weight to one end, so the center of mass definitely will not be at 50 centimeters. And let's see what happens this time. See, she's not watching her fingers. She's not purposely doing this. It's just that's what always ends up happening. Now, we haven't calculated out the center of mass, but clearly the object is balancing, so it must be pivoted at the center of mass. So it's somewhere right here. So try it sometime. I've done it with a hammer. You can get a hammer and it works just as well. Your fingers will naturally slide together to the center of mass. Here's some practical application for this. Stability is obviously very important for automotive manufacturers. In the case of a vehicle stability, the base of support is actually this entire wheelbase. The center of mass of a vehicle is usually about in the center. If the vehicle were to start to tip, as long as the center of mass is over this support base, this wheelbase, then the car will naturally rotate back and settle down. So that's caused by torque due to gravity. So this is non-zero torque causing it to rotate back until it's able to settle down. A critical point happens when the center of mass is directly above the only remaining support base, that point right there. So we call that critical because a tiny increase is going to tip it over, a tiny decrease is going to let it rock back down, well, relatively safely. Okay, so this is what that's showing here, is the center of mass is now not over the support base, so gravitational torque is going to cause it to roll over. Well, you can play around with this. If you have an object that has a high center of mass, you can make it more stable by increasing its base of support. If you have an object that has a small base of support, then you can make it stable by lowering its center of mass. That gives it more range of motion before the center of mass is in this area out here or out there. Same thing up here. By giving a wider base, it increases the range of motion, so the center of mass can go that whole distance before it falls over. Okay, so this would probably be the least stable of the two, because it has a high center of mass and not necessarily a high base of support. So there's actually quite a bit of mathematics and geometry that go into this, and automotive manufacturers do take this seriously. They go through all the math and they make sure that they're, well, at least they're supposed to be making sure that they're building as safe a vehicle as they can. So let's wrap this up with the definition of stability. In general, as long as the center of gravity remains over the base of support, torque due to gravity will rotate the object back to a stable position. So we call that stable. All right, just to see if this is clicking, imagine this bar is freely rotating on top of this triangle, and a girl is standing on it one-footed. The way they're set up right now happens to be equilibrium, which means zero acceleration. So they're at rest at the moment. So the question is then, where is the center of mass of the girl/bar combination? Well, hopefully it's clear by now. It's got to be directly above the base of support, and in this case it's just that tiny little spot. So the center of mass is probably right here. Remember, again, it doesn't have to be a physical point on the object. It's just a theoretical location. Last example. In our discussion of rotational inertia, I showed a picture of a tightrope walker, and I said that they use those poles to increase their rotational inertia, and that's true. It makes them less or more resistive to changes in rotation. But after our recent conversation, can you think of another benefit to having a pole shaped like this? Well, the answer is related to center of mass. So the center, if the pole is drooping like this, that's going to lower the center of mass of the total combination, which again makes the person more stable. So there's a rotational inertia benefit and center of mass benefit, assuming that it sags like that. I hope this has given you a better understanding of center of mass. Chapter 8 is a long chapter. There's a lot of material in it, so we're going to break it up over a couple of days. In the last set of videos, we'll discuss centrifugal force and angular momentum.